Good evening, and today I will be looking at the fourth and final extra credit question, as well as the fourth and final potential question on the upcoming test number 4 for Chemistry 1412. This problem has us looking at two different trisub cyclohexanes, which are depicted here in this case, and the question asks us to determine which has them, or of the two stable conformers, which is more stable, and then between the two most stable conformers, which is the most stable. As in, like, the structure, the two chair diagrams from here to determine stability, which one's more stable between those two, and then which one's more stable between those two, and which one's more stable between these two. I'll get into the nitty-gritty of that momentarily, but I've gone ahead and drawn two trisubcyclohexanes as well as boxed their complicated substituents to illustrate over here to see what I'm meaning, so we can get where we need to go before actually getting to the chair diagrams themselves and determining stability. Because first things first, we need to name the two compounds so that we know where to put everything. So in this red box here, I have a carbon going on to 3 carbons. So let me just draw it here. So we have, this is the parent carbon, and it's going out to a carbon, which is then going out to 3 different carbons, which on each of those has 3 CH3s. So it's a little convoluted here, but it gets you to work with substituents that you aren't used to. And of course, in the actual chair diagram itself, I won't be trying to draw this whole thing, because it could get too convoluted for the sake of our chair. Alright, so this is what you have every time you see a little red box, or every time you see CCH333, which is an interesting way to read that. Anyway, in the green, I have this kind of simpler one, where you have the parent carbon here. You have a carbon going off to just 3 CH3s. So essentially, with the red boxed one, you have a carbon going into 3 of the green boxed substituents. So that helps you kind of illustrate, and it'll help us in naming as well. Alright, so in terms of naming, I'll go ahead and start with the more complicated one over here, the one with 2 complicated substituents. So we have the longest cycle being the 6. So we have cyclohex to start out with. We don't have anything other than single bonded carbons and hydrogens, so we can just go ahead and say that this is an alkane, making this ane. So we have cyclohexane as our parent, and that is the case for both of them, so I'll just go ahead and write it here. Now in terms of naming the substituents, let's go ahead and identify them first, as in where they are. And then we have to determine a name, we have to determine a numbering system. Now this, you want the lowest number in the first point of difference. And so by numbering, I can determine that the numbering system will be something like this. Now of course you could number it every way under the sun, but for simplicity's sake, since this is already a very, very complicated question, it's best to just, kind of number it off camera and find out the best numbering system here. Alright, so we have a substituent at 1, at 2, and at 4 for this, and now we just need to find out what each of those are. So whenever we determine complicated substituents, we usually tend to kind of go back to them And in this case, 1 and 2 are both complicated, so I'll come back to them. But we can see that 4 is just a simple methyl group. So under 4, I can write methyl. Alright, so a good thing about writing, or about drawing these two diagrams over here is that we can use them to help name. So I'll start with the CCH33 right here. So this is part of the parent, so we don't count this carbon. We always want to start at 1, at the conjoining carbon, and then we can really go anywhere with the rest of it. So we can have 2 be here. So we want to circle that longest chain. So this parent will be eth, and then since it's a substituent, it will be ethyl. And we'll write that at the end later, because at 1 we have 2 methyl groups for the substituent. So at 1 we have this methyl and we have this methyl, meaning at 1 and at 1 we have methyl. Or we could say that we have 1,1 dimethyl, and then we'll put ethyl there. So the name for this substituent will be 1,1 dimethyl ethyl. So every time we see this green box, we can know that we have 1,1 dimethyl ethyl, and that is at 1 in this case. So we have 1,1 dimethyl ethyl. Alright, now we get to the slightly more complicated one. So over here we have the parent carbon, which we don't count. We always start with this one at 1, and then numbering from here gets a little bit crazy. We want to pick the one with the most branching, but I mean, it will be 2 in each case. So we can kind of just go along the same path as we did the other one, 2 and then 3. So if this is our longest chain, which it is, then we have, oh boy, all of these substituents. That's an ethyl with methyls on. Yeah, they're pretty much all complicated substituents from here. So here we have 2 methyls. Here we have a complicated substituent. And then here we have another complicated substituent. Alright, so let's get started. We can restart here by saying, we'll name this first. So we have this, the parent itself being prop, and then it is a substituent, so we'll call it propyl. And then we have at 1 a complicated substituent, at 1 a complicated substituent, and then at 2 we have 2 methyls, so I'll just say dimethyl for time's sake. So we can see that at 1 we have 2 of the same substituent here, which involves 1, 2, which involves an ethyl with 2 methyls on the end. So we can say, excuse me, we can say that we have 1,1 dimethyl ethyl, and then we have 2 of those. So I believe you could write like this, but I mean, just so I don't confuse anyone, because I'm unsure about this particular one, I'm going to write it twice, but you could probably write di in front of it or write squared, but to be safe, you can always just write it twice. I don't believe any points will be counted off, and this is an experiment's sake, because this is a rather complicated substituent, more so than what we're used to. So, in that case, The name of this substituent will be, we have 1, 1, 1 dimethyl ethyl. We have 2 of those, and just for sake of space, I'm going to write that. And then at 2, we have a dimethyl. And then that'll come down into propyl. So it's a very, very long name for that substituent, which will end up going at the beginning. But, of course, this whole process is just to identify where each of the substituents are. The problem is less concerned with naming than it is knowing like where this is, and so I will do the same here, just for sake of time and for sake of simplicity. So over here, we also have to do a numbering system, and we'll also end up with 1, 2, 3, 4. So 1, 2, and 4. And because we don't need to name things here, we just need to find out which is the more stable. We can call this number 2, and we can call this number 1 for sake of simplicity. Again, the question is simply asking to find the most stable conformer. And so naming is good practice, of course, but it's not required for the question. So for sake of time, for sake of space, we will continue on. Alright, so drawing chair diagrams to represent both of these. 3 things you should know. 1, when drawing a chair, you always need to draw chair flips, no matter what. So each chair diagram is really 2. And then 2, you want the largest or most groups on equatorial. That's to find stability. So starting with what we'll call atom number 1 here, we can go ahead and draw our chair. And then we can start at 1 here. We can go ahead and number. And then we can draw all of our equatorial because we know that they're going to be alternating. I'm sorry. I messed up there. Give me a second to recollect my thoughts. I'm sorry. So, back to the question. What I forgot to mention is that we need to assign a direction, not whether axial or equatorial, to both the dashes and the wedges. And so, in lieu of that, we have a dash at 1. And since I typically assign dashes to being down, and 1 is usually down, that kind of threw me off in my first one, so I just had to take a moment there. Be sure to do this before you start drawing so you don't confuse yourself like I did. Anyway, now we have to start drawing the equatorial bonds. I do all of the bonds out of practice, at least for axial. That's kind of force of habit. But for the equatorial ones, I'll just focus on the location of the substituents. So we have an equatorial down at 4, which is where the CH3 will be. And then we have an equatorial up at 1, which is where the CCH3 will be. And then at 2, we have an equatorial down. Alright, so really you should just focus on the location of the substituents for sake of space, for sake of time. And that's what I will be doing from here. So on this dash that we have at 1, you want to be sure to follow the the marking, not which direction it looks like it's going. And you want to follow direction, not you want to assign the symbol to direction, not equatorial or axial. So at 1 we saw that we have a dash which is going down, so we'll have CCH3, 3. And then this will just be a hydrogen. At 2 we saw a dash here, or sorry, a wedge. And so going up, we'll have a we'll have the CCH3, 3, 3. We'll have this thing. And then on 4, we saw that we had a dash. So on the drawing here, the one going up, which in this case is an axial, we'll just have a simple methyl group. Alright. So drawing the chair flip. The chair flip is drawn simply by reversing the parallel lines, and then drawing from the same way there, keeping the same numbering system. So this will be 1, 2, 3, 4, 5, and 6. Always be consistent in the way you number, especially whenever you flip, so that confusion doesn't set in. Alright, so I'm going to use red to represent the axial now, because the equatorial shift into axial bonds, they will stay the same direction. So at 1, now we will have an axial bond going up. At 2, now we'll have an axial bond going down, because these equatorial shift. That's what happens when a chair flips. And then at 4, we'll have an axial going down. Alright. So this axial here at 1 will shift into an equatorial bond at 1, going down. This axial bond here at 2 will shift into an equatorial bond at 2. This axial bond going up at 4 will stay going upwards. It's just going to be an equatorial bond. So always remember to keep direction, but just change what it is itself. And color coordinating in this particular case always helps. So now you just move your substituents onto the same, in my case, color, but in your case, the bond that's shifted, you'll just keep it on that same bond. So the substituents themselves don't actually shift bonds; they just shift. They just shift with the bond itself. Yeah. Alright, so to determine the more stable conformer between these two chairs, we'll say that this one has 3 axial bonds with the substituents, because all of these are axial, which means it has no equatorial, while the bottom one has 0 axial with 3 equatorial bonds, because all of these substituents are equatorial. So this one is clearly the more stable, because more equatorial is more stable, and also the larger atom groups being on equatorial yields greater stability. Alright, so now we will move on to the other one, which is done in the same manner, so I will just do it on camera for sake of time. Alright, so after drawing my 2 correct chairs, disregarding this one, because I messed up again, as I'm prone to do, we can see that this one will be the more stable, not because it has more equatorial, but because it has a larger atom group on the equatorial bond. Stability requires that the largest atom group is on the equatorial bond so that there's less repulsion, because larger atoms have larger electron clouds, so they have more repulsion, and equatorial bonds are just kind of farther away, so they prioritize, especially a large atom group like this one, to be on an equatorial bond. And that is compared to this one, which has, yes, it has 2 equatorial bonds, but the large atom group is not on one, and that kind of makes the atom kind of upset. So this would be out of the question. Between these two, it's fair to assume that this, with the large atom group and the more groups on equatorial, is more stable than just the large group on equatorial. So with all the atom groups on equatorial, you have the most stable conformer right there. So of the two trisubcyclohexanes, you have this one and this configuration as being the most stable conformer. Thank you for watching, and sorry for running so long.